Welcome. Today we explore why the speed of light, denoted c, is the cosmic speed limit. From the 1905 postulates of Einstein's special relativity to modern experiments, everything in physics tells us nothing with mass can reach or exceed c. We will break down the concepts with clear examples and equations. In the late 19th century, scientists assumed light needed a medium, ether, and thus its speed would change with motion. But Michelson and Morley measured light in different directions and got a null result. No difference was found. This unexpected outcome implied there was no preferred frame, suggesting the speed of light is the same for all observers. Einstein later used this to build special relativity. Einstein proposed two key ideas. First, no inertial observer is special. The laws of physics are the same whether you're standing still or moving at constant velocity. Second, the speed of light in vacuum is always the same number c, regardless of the motion of the source or observer. These principles force us to rethink space and time. To keep c invariant in all frames, time and space must mix in a precise way. The Lorentz transformations above, with gamma defined as 1 over the square root of 1 minus v squared over c squared, relate coordinates in one frame to another. This yields several surprising effects, as we'll see next. First, time dilation. A moving clock ticks slower. The proper time interval, delta tau, measured on the moving clock, relates to the dilated time, delta t, equals gamma delta tau. For example, cosmic ray muons created high in the atmosphere travel near c and live about 40 times longer, as seen from Earth, than at rest. Time actually stretches by factor gamma, preventing a moving clock from ever catching up to a stationary clock if it tries to reach light speed. Similarly, rulers moving relative to you appear shorter along the direction of motion. The contracted length is L equals L0 divided by gamma, where L0 is the rest length. These effects keep the speed of light consistent. Clocks slow and lengths contract so that every observer still measures light as c. Even when combining velocities, you can never exceed c. Instead of simple addition, relativity gives u equals u prime plus v over 1 plus u prime v over c squared. This ensures that no matter how fast you add speeds, the result is always less than c. In fact, theory demands this. No object's speed can exceed the speed of light. You could chase a flashlight in a super-fast car, but you would still see light racing ahead at c. Einstein's famous formula E equals mc squared tells us mass and energy are equivalent. In a moving frame, the total energy is E equals gamma mc squared. Thus, as v approaches c, gamma approaches infinity, and so E approaches infinity. This means to accelerate a massive object closer to c requires ever more energy. In fact, as DOE notes, an infinite amount of energy is required to make an object move at the speed of light. It is impossible for any matter to travel faster than light. Consider that gamma equals 1 over the square root of 1 minus v squared over c squared becomes infinite as v approaches c. This translates into an infinite kinetic energy requirement. CERN accelerators get protons to more than 99.9% of c, but adding energy yields diminishing returns. Mass effectively grows without bound, so no finite fuel can push a spaceship to light speed. Many experiments have tested the speed limit. High-energy accelerators push particles very close to c, but never past it. In 2011, the Opera experiment briefly reported faster-than-light neutrinos, but later found experimental error. Such claims are viewed skeptically because special relativity has passed every precision test. Even cosmic rays, GZK limit, obey the limit. So far, no observed particle with mass breaks the c barrier. Theory warns that if something could travel faster than light, strange things happen. Causality breaks down. Einstein's relativity implies superluminal travel would mean an effect could precede its cause. As one article explains, if something travels faster than the speed of light, it goes backwards in time. This would violate the basic rule that causes come before effects. Such paradoxes, including meeting your past self, argue strongly against real FTL objects. Photons and other massless quanta always move at c in vacuum by definition. They have no rest mass, and their entire energy is kinetic. Everything else with mass must travel slower. In fact, as Wikipedia notes, particles with non-zero rest mass can approach c, but can never reach it. Light is the speed limit, and massless things ride right at that limit. Maxwell's equations, 1865, predicted that electromagnetic waves propagate at c, determined by vacuum constants, permittivity E0 and permeability μ0. This showed c is set by fundamental physics, not a medium. Maxwell's work hinted that c was deep in nature. Einstein later postulated this c applies to all observers. In Minkowski spacetime, each event has a light cone. The boundary at 45 degrees is defined by signals moving at c. Events outside one another's light cones cannot influence each other. This geometric picture shows why c is the maximum speed. Space-like separated events outside the cone cannot be connected by any cause-effect chain unless c were exceeded, which relativity forbids. Even GPS satellites confirm relativity, time dilation, without altering c. Satellite clocks tick at different rates due to speed and gravity, and corrections are needed, yet signals still travel at c. In practice, no information in systems like GPS or Internet ever outruns light. DOE notes GPS must account for relativity in timing, but still obey the c limit. A common question: doesn't quantum entanglement imply FTL effects? Actually, no. Measurement outcomes are correlated instantly, but you can't use that to send a message faster than c. The no-signaling theorem guarantees that entanglement never violates the relativity limit. It's a subtle quantum effect, but it doesn't break our universal speed limit. Even in gravity, c is key. Escaping a black hole's event horizon would require going faster than c. DOE explains, special relativity holds that speed of light is the same across the cosmos. Escaping a black hole would require an object to move faster than light. So black holes literally trap light because nothing can surpass that speed limit. How about the accelerating expansion of the universe? The fabric of space can stretch so fast that distant galaxies recede from us at an apparent rate exceeding c. But this isn't local motion through space, it's space itself expanding, As Wikipedia clarifies, objects can appear to recede faster than light due to expansion beyond a certain distance, but this does not allow information or matter to outrun light locally. It's a loophole that doesn't violate relativity. Some theories have imagined particles called tachyons that always move faster than light. However, none have been observed, and they lead to severe causality issues. If tachyons existed, they would require imaginary mass and cause paradoxes. Mainstream physics treats them as speculative. All experimental evidence so far supports that no real particle exceeds c. Why is violating c such a big deal? Because faster-than-light travel implies time travel to the past. For example, in some frames, a return FTL signal could arrive before it was sent. This upends causality, grandfather paradox style. Relativity tightly links c to the structure of spacetime to prevent these paradoxes. In practice, physics conspires to forbid FTL, so we don't rewrite history. Scientists continue testing c's constancy. For example, precise timing of gamma rays from distant cosmic sources checks if higher energy light might travel at different speeds. Recent studies found no variation. Einstein's constancy holds to better than 1 part in 10 to the 18. Special relativity remains robust even in extreme conditions. Lorentz invariance is at the heart of modern physics. It means the form of physical laws doesn't change when switching between uniform velocity frames. Electromagnetism, quantum field theory, and even the Standard Model all assume no preferred frame. In fact, Science Daily points out that after 100 years, tests of Lorentz invariance have only tightened the bounds. No breakdown has ever been seen. Einstein famously asked, "What if I rode alongside a light beam?" Classical thinking would say you'd see a frozen light wave, but Maxwell's equations forbid standing light. The only resolution is that you cannot catch up to light. It always moves at c. This simple thought experiment hints at why c is invariant. On the board we have the essential equations of special relativity. Lorentz transformations, the Lorentz factor gamma, velocity addition law, and energy-mass relation. These mathematically enforce the speed limit. Students should note how each formula breaks down singularities or infinities as v approaches c, illustrating the insurmountable barrier. Let's do a quick demo, conceptual animation. 2 lightning strikes hit the ends of a train simultaneously for a ground observer. For a passenger moving toward one strike, relativity tells us the events are not simultaneous in their frame. This relativity of simultaneity ensures all observers still measure c, but agree on cause-effect order within light cones. It's another subtle consequence of c's constancy. What does this mean for technology? Particle accelerators factor in relativity to reach high energies and never see particles move at c. Astronomers account for light travel time when studying the universe. GPS engineers correct for time dilation. All these are consistent with c as ultimate limit. In other words, relativity isn't just theory, it underpins modern systems, always respecting that speed cap. Finally, why is the speed of light the special speed? In relativity, c emerges from the geometry of spacetime and the structure of Maxwell's equations. It's simply the invariant conversion factor between space and time units. No physics law forbids a different invariant speed. We define meters and seconds so that that speed is the distance light travels in 1 vacuum second. Thus, it's built into nature's fabric. A few clarifications. Light does slow in glass or water, but only because it's being absorbed and re-emitted. Between atoms, it still moves at c. And no matter how empty space is, nothing with mass goes faster than c. Claims of FTL often involve misleading notions. For example, moving a laser dot on the moon can outpace light, but that dot isn't a physical object. All realistic scenarios obey the limit. In summary, the speed of light is woven into the laws of physics as the maximum speed. It stems from Einstein's postulates and Maxwell's theory, and is enforced by the mathematics of relativity. Everything we know, experiments, cosmic observations, and practical technology, aligns with the conclusion nothing with mass can reach or exceed c. Our chalkboard is full, but the concept is clear. C is the ultimate speed limit of the universe. That concludes our journey through the speed limit of the cosmos. In the remaining time, let's discuss any questions. Why does nature enforce c as a limit? Is there room for new physics? Remember, future experiments like gamma-ray observations will keep testing this limit. But so far, every result reaffirms Einstein's postulate. The chalkboard may end here, but physics always moves forward, at or below c, of course. Thank you.